in some books they have been mentioned the lens antenna. So you can see the antenna and electric field lines. So here is the transmission, this is the source section, this is the transmission line section, this is the actual antenna part which convert this guided electrical signals into the free space waves, and these are nothing but the radiated free space waves uh, that is obtained from this antenna structures. Now here we will understood the radiation mechanism. The radiation mechanism is nothing but uh, we know that if a charge is not moving, current is not created and there is no radiation. If the charge is moving with a uniform velocity, then there is no radiation if the wire is straight or infinite in extent. There is a radiation if the wire is curved, bent, discontinuous, terminated, or truncated, as shown in the next slide. This is the curved structure. This is the bent structure. This is the discontinuous wire and the terminated wire with some load. This is the truncated. So these structures radiate effectively because a constant current cannot make the radiations from the structures. For that, we need a conducting wires or material whose prominent characteristic is the motion of electrical charges and the creation of current flow. If a wire is made of ideal electrical conductor, the current density resides on the surface of the wire and it is given by J is equal to Q into V, where Q is the surface charge density and the wire is very thin, ideally the zero radius, then the current in the wire can be represented as I is equal to Q into V, where Q is nothing but the charge per unit length. So instead of examining all current densities, we can concentrate on the wire where di by dt is equal to q into dv by dt, which is q into v. So that is nothing but qv is equal to kv produces radiations. It follows that di dt produce the rate of change of current produces the radiation. So if the charges are transients and pulses, use currents for time harmonic variations. Therefore, to create radiation, there must be a time varying current or there should be acceleration or decelerations of the charges. So as I stated earlier, if there is no charge, is not moving, current is not created and there is no radiation. If the charge is moving with a uniform velocity, there is no radiation if the wire is straight and infinite in extent. There is a radiation if the wire is curved, bent, discontinuous, terminated or truncated, as shown in the slides. If the charge is oscillating in a time motion, it radiates even if the wire is straight. So you can see here the curved wire, the bent wire, the discontinuous wire, terminated wire, truncated. So now let us move towards the very important section of the radiating system, that is the field regions. Field regions are nothing but the near field and far field of the antenna structures. These antenna structures, every antenna have the two fields. One we call it as a near field and one we call it as a far field. The actual radiation is always in far fields. So Every time the space surrounding an antenna is usually subdivided into three regions, that is the reactive near field, the radiating near field, this is reactive near field, the radiating near field, and after radiating near field there is a far field as shown in figure. These regions are also designated to identify the field structures in each. So in reactive near field region is defined as the portion of the near field region immediately surrounding the antenna where the reactive field top predominates. For most of the antenna, the outer boundary of this region is commonly taken to exist at a distance r, which is less than 0.62 under root of d cube by lambda from the antenna surface, where lambda is the wavelength and d is the largest dimension of the antenna. For a short dipole or equivalent radiator, the outer boundary is commonly taken to exist as the distance of lambda by 2 pi from the antenna surface. Now there is a radiating near field region is defined as the region of the field of an antenna between the reactive near field region and the far field region where radiation predominates and wherein the angular field distribution is dependent upon the distance from the antenna. So if the antenna has a maximum dimension that is not large compared to the wavelength, this region may not exist. For an antenna focused at infinity, the radiating near field region is sometimes referred to as the Fresnel region on the basis of analogy of optical terminology. If the antenna has a maximum overall dimensions which is very small compared to the wavelength, the field regions may not exist. The inner boundary is taken to be by the distance, that is r is greater than 0.62 under root of d cube by lambda, and the outer body, the distance r less than 2d square by lambda, where d is the largest dimensions of the antenna. Now for the far field region is defined as that region of the field of an antenna where the angular field distribution is